Hey everybody, it's Mrs. Mancuso, Merm here, ready to do this physical behavior of matter. So we are starting out with part one, understanding a lot about heat. So just a reminder, as I go through this, there will be some parts where I do a little bit with you and you've got to finish up some parts on your own. And there'll be other parts where you might just want to pause me so you can either write down some stuff in your notes or take the time to do the work on your paper. When we get to the calculations, definitely pause me so that you try the calculation yourself and then see if you got the same answer as me. All right, so let's get started here. We're going to start with temperature. So when we typically think of temperature, well, we live in America, so we think of Fahrenheit, but in the metric system, we use Celsius, and we even use another temperature, which we're going to learn today, called Kelvin. So for a lot of the work that we do with gases, we need to make sure the temperature is in Kelvin, not Celsius. So the way you do that is you add 273 to your Celsius value. So Kelvin is going to be degrees Celsius plus 273. So the distance between two measurements in Celsius is going to be the same as the distance between two measurements in Kelvin. Kelvin's just always 273 steps ahead. So let's get started here on our math. This is one of the ones I'll do just a couple with you. So if it's 0 degrees Celsius, I add 273. So this would be 273K. So this one, if it's 100 and I add 273, that's going to be 373. And this one, if it's negative 10 and I add 273, it's going to be 263. All right, now I'm going to do a couple over here. So this time, in order to get this side, you have to go K minus 273 is going to give you Celsius. So if I take 100 and I minus 273, I get negative 173. And that makes sense. That's definitely going to come out a negative number because 100K is less than 273, so it has to be less than 0 Celsius. All right, so if I take 300 and I minus 273, that comes out 27 degrees Celsius. All right, so you get the hang of that. So work on that and well, pause me, work on that, and you can check your answers when you're done. I'm going to move on to the next slide. So heat transfer. This is something that you've probably understood since you were little, that heat always moves from an object with a warm temperature to an object with cooler temperature. So it always goes from warm to cold. So you guys know my hands are always freezing in the room. So if you grab my hand, heat would go from your hand to my hand because my hand is colder. All right, draw an arrow to indicate the movement of heat in each of these four pictures. So I'm going to do this picture with you first. So here's a hand in the snow. So the hand is definitely warmer than the snow, so heat goes in this direction. And then here's one with ice and water. The ice is colder, so the heat is going to go from the water to the ice cubes. Okay, and then you can do them over on this side. All right, let's keep going. Temperature and phase change. So if you have a solid, a liquid, and a gas. So let's just write on top of each one of these. I want a new color. All right, so here is my solid, and here is my liquid, and here is my gas. So if I have a solid, think about a solid as the molecules be really close together. They have strong attraction between the molecules. They take up a definite volume, a definite shape, and they're not compressible, like you can't change them. If you add heat, you are doing melting right here. If you melt it, the liquid molecules are now going to be still close together. Wait, I'm drawing too many. 1, 2, 3, 4, 5, 6, 7. All right, I'll make 8. And I'll add 2 more over here to have 8. Okay, so a solid looks like a regular geometric pattern, whereas a liquid it'll take on the shape of the bottom of the container. At least it still has a definite volume. Like if you had 100 milliliters of water, it wouldn't matter if you poured it out from a beaker to the desk, it's still 100 milliliters. So it has a definite volume. It just takes the shape of the bottom or potentially more of the container that it's put in. And now if I have a gas, so what I'm doing to change it from a liquid to a gas is I'm boiling it. And now the molecules will all be separate. So I still need all 8. 1, 2, 3, 4, 5, 6, 7, 8. But this time they really spread out and they occupy the entire container. Now, one of the words that I mentioned was compressible. Only a gas is compressible. Liquids are not compressible, solids are not compressible. But a gas, I could actually put pressure on this and I could make those molecules fit in a smaller volume. So the volume can change for a gas where it can't change for a solid or a liquid. A solid, we like to say that these molecules have the most strong attraction between them. And over here, a gas, these molecules have the weakest attraction between them. All right, so on this slide, we are removing heat. So this time you are going from a gas to a liquid to a solid. So when you go from a gas, well, let's only do 6 this time. 1, 2, 3, 4, 5, 6. When you remove heat, so this is an exothermic reaction. 1, 2, 3, 4, 5, 6. In order to do that, you are taking away heat and you are condensing. All right, so like condensation forms on the mirror after you've taken a shower because the water vapor, the gas molecules are colder out away from the shower by the mirror and they condense. And then to change the liquid to a solid, you have to freeze. So this is if I am cooling. So this is all of a cooling action and the last one was all heating. And my solid, I want my 6 to be strong attraction, close together, regular geometric shape. All right, let's move on to our next slide. So here is what we call a heating curve. Heating curve. Sorry, it's a little hard to write on here. So I am starting off, my temperature is actually a measure of kinetic energy. So think of kinetic energy as energy in motion. Here, it's very little motion. So it's colder temperature here, and here it is a solid. And over time, if I heat up this solid, it will eventually reach this point on the graph, which is the melting point. And when it reaches the melting point, you have both a solid and a liquid until that melting point is done. And you will notice the kinetic energy changed. It increased as you went up from F to E. But as you went across E to D, it stayed exactly the same as it melted. So the kinetic energy stays the same right here, but the potential energy increases. So there is greater potential. You are adding heat to it, but that heat is not making the temperature go up. So it's not changing the kinetic, it's changing the potential energy. And so this is where it is melting right here. All right, once it's melted, this bar is all liquid. So D to C is all liquid, and now we're heating it up again. So this would actually happen if you took a block of ice and you put it in a beaker. It would heat up until it hit 0, the melting point, and then it would melt and it would stay at 0 for as many minutes as it took to melt it. And then as soon as it became water, now you'd be able to heat it up again. So the temperature would go up again. So the kinetic energy goes up again from D to C. And then when you hit C to B, it's changing into a gas. So this temperature across here, this would be the boiling point. So here it is boiling. And when it is boiling, the kinetic energy is the same, but the potential energy is increasing. And here I would have both a liquid and a gas because it's changing. And by the time I got to this section, by the time I got to B, it would be all gas. And so you're heating the gas again in the B to A section. So if I do this again, I'm going to just take this yellow highlighter color and I'm going to say here, here, and here. This is going to represent my kinetic energy is going up and the potential energy is going to stay the same. I'm going to take this green color and show here and here on those sections, the kinetic energy stays the same and the potential energy goes up. And it'll also help you if you think and remember that kinetic energy is a measurement or temperature is a way to measure kinetic energy. It'll help you with that part of the graph. All right, let's move on. Melting point. So I need a new color here. Melting point is the temperature at which a solid changes to a liquid. You might be like, Merm, what are we doing today? We know all this stuff already. And it's really some of the beginning of this unit is a good review. So just think of it as like a nice little review day, but we're going to get into some new stuff coming up here soon. All right, as the heat is added, temperature will stay the same until the substance is entirely melted. So that's why we have that plateau. So like here, it was a solid, and here it's a liquid. Here, the temperature doesn't change while it's melting. All right, the kinetic energy stays the same, but the potential energy is increasing as it melts. All right, we can look up melting points right on table S. So if I go across from, I have my reference table right here, of course. If I look at hydrogen, it melts at 14K, or lithium melts at 454K, or calcium melts at 1,115K. So I can look up melting points. All right, boiling point. Boiling point is the temperature at which a liquid changes to a gas. As the heat is added, temperature will blank until the substance is entirely vaporized, so it will stay the same. So if this is a liquid, here it's a gas, this is my boiling point. That is when it is boiling or vaporizing. The kinetic energy is staying the same because I have a plateau. The potential energy is increasing because I'm still adding heat, but the heat is going to the potential. So here is my table S. So on table S, here's my melting point, here's my boiling point. So for any one substance, let's look across, let's do sodium. All right, so for sodium, sodium melts at 371 and it boils at 1156. So any temperature lower than 371, it's going to be a solid. And if the temperature is between 371 and 1156, it's going to be a liquid. And if the temperature is higher than 1156, it already boiled, so it's a gas. So I could give you any temperature right now. I could say like, oh, what if it is at 500K? You would say, okay, 500 would fall right in here, so it would be a liquid. Well, what if it was only 200K? All right, 200 is before the 371, so it would be a solid. And what if it's 1500K? 1500 would be after the boiling point, so it has changed into a gas. So that's how you figure out if anything on the periodic table at a certain temperature is a solid, a liquid, or a gas. So I have two more examples and I found some cool diagrams for you. So first of all, here it is a solid, and here it is a liquid, and here it is a gas. So here, this change right here is its melting point, and here it is boiling. So we got to go look up iron. All right, so we go back to here. Oh, actually, I didn't put it on the screen. So I got to grab my reference tables. Iron is element 26. So element 26 melts at 1811K. And it boils at 3134K. So if I have a temperature lower than 1811K, it's going to be a solid. And if I have a temperature that is between 1811 and 3134, it's going to be a liquid. And if I have a temperature hotter than 3134, it is going to be a gas. Wow, that's insanely hot. All of this is crazy hot. Even just melting it, that is so hot of a temperature. All right, now I picked a different one, nitrogen. So here it's a solid, here it's a liquid, here it's a gas. So to do this, I have to melt it, and to do this, I have to boil it. So now I'm going to look up nitrogen. So nitrogen is actually on this one. So here's nitrogen right here. And so 6377. All right. 6377. And remember, this is always in K. So that means anything less than 63K is going to be a solid. Anything between 63 and 77K is going to be a liquid. And anything greater than this is going to be a gas. That's how you read it. So here is some practice. I'm going to do just the first one with you, and I'm going to have you do the rest of them. All right, so first thing I want to do, use your reference table to determine the phase of matter for each substance at the given temperature. So we want to go to aluminum, that's element 13. And I want to go across and I want to see where is it at 1,000 degrees. So I see that aluminum melts at 933. Well, we're over 933, so it's not a solid anymore. Now it's a liquid. It doesn't boil until 2,792. So that means I'm between the melting point and the boiling point. So that means that I have a liquid. So you're going to go ahead and do that for these other four. So you can pause me right now. And now I'm going to do one of these bottom ones with you. So convert the given Celsius temperature to Kelvin. So if I have 500 degrees Celsius, I add 273. So that would be 773K. And now I look up Hg. Hg is mercury. Mercury is number, let's see, got to find it. Number 80. So I go over here. Mercury melts at 234K. So we're over 234. So it is not a solid. And then it boils at 630K. So if we're at 773, it's already boiled. So this is going to be a gas. All right, so that's how you do it. I want you to pause me again and do the work. So go ahead, do the next one. All right, moving on to another heating curve. So this time it is blank. So I just wanted to go over it one more time with you, another little refresher. The first thing I want to do is I'm going to fill in, this is going to be temperature, and this is going to be time. Here I have a solid, here I have a liquid, and here I have a gas. I'm going to use another color, and I'm going to show this right here. This is where it melts. And melting, a new word for melting, it's also called fusion. So right here, this would be the melting point. And then up here, at this point, it is boiling. We said another word for that is vaporization. So right here, this would be my boiling point. All right, during the yellow and the green. So this and this, my potential energy is increasing, but my kinetic energy is staying the same. And then let me use this blue color anywhere that I have slope. anywhere that I'm changing temperature, here the kinetic energy is increasing and the potential energy is staying the same. All right, so I just want to go over that one more time with you. And here's some questions. So the first one, what is the melting point of this substance? So I know melting point is going to be right here. So I go across, it's right there. So that is 50 and we're in degrees Celsius. So 50 degrees Celsius. And then to convert it to K, I have to add 273. So 273 plus 50 is 323 K. All right, how long does it take to melt? All right, it starts melting at 2 minutes and it's done at 5 minutes. 5 minus 2, it took 3 minutes to melt. What is the boiling point of this substance? All right, boiling is up here. So if I go across, it's right there. So it's 110 degrees Celsius. Converted to K, so I add 273, so that would be 383 K. How long does it take to boil? Okay, it starts boiling at 10 and it's done at 14. 14 minus 10, it takes 4 minutes. All right, what if you had a larger sample? What would change? Okay, the boiling point would still be the exact same temperature and the melting would be the exact same temperature because those are published in your reference table. So those don't change with mass, but what would change is the amount of time needed to heat, melt, and boil. So think about it as like if you had a little kiddie pool in your backyard, how long would it take to warm up to be warm? Would be really different than if you had a huge pool. So the amount of water, the mass of the water would change that amount of time, amount of heat required. All right, so this one is what we call a cooling curve. Cooling means you are starting off at a really high temperature. So again, here's temperature, here's time. So here it's very hot. So you start with a gas, move to a liquid, move to a solid as you bring down the temperatures. You still have two plateaus. This one right here is going to be condensing. And this one right here is going to be freezing. This is still the boiling point. The only difference is I'm going down instead of up, but it is the exact same temperature. And the freezing happens at the melting point. So the melting point is just the temperature at which you can change from a liquid to a solid or a solid to a liquid. So right now we aren't melting, we're freezing, but it's the exact same temperature. All right, and then again, where I have this, my potential energy. Okay, I know that it is changing, but this time it's not going up, it's going down because you're taking heat out. And the kinetic energy is staying the same because you're on a plateau. And then here in this section, and this section, and this section, the temperature is going down. So here, the kinetic energy is decreasing, but the potential energy is staying the same. All right, so I just want to make sure that we did one where it was cooling as well as heating. All right, so now we're going to learn how do you calculate heat. So heat is equal to Q. And there are 3 different formulas that you're going to use based on what's happening in your question. So Q equals MC delta T. All right, Q is heat, M is mass, C is specific heat capacity, delta T is the change in temperature. So this first formula, I'm going to mark it with a 1. If I am on this section of the graph, this section of the graph, or this section of the graph, I am going to have a 1 here. I'm going to use that formula. I'll just do it in purple. So any part on the graph where I'm just changing the temperature, that's how I calculate the amount of heat. I'm going to have to multiply the mass by the specific heat, which is a value, by the change in temperature. All right, let's say that now I want this Q equals MHF HF means heat of fusion. You'll remember fusion is where something melts or freezes. So if I am on this section of the graph and only this section of the graph, that is where I use Q equals MHF. So the heat of fusion is an actual value. It's right in your reference tables, just like C is, and you're going to look it up and use that value. And then let's say right here, this one, Q equals MHV, heat of vaporization. Vaporization is where something boils. There is my boiling section of my graph. If I am trying to figure out the heat from boiling or condensing or vaporizing, I am going to use that formula. So those are my formulas. These are right on table T. You don't have to memorize them. Okay, this is actually a little practice activity for you to make sure that you understand the differences between solids, liquids, and gases. So you take each one of these little guys. So strongest attraction between molecules. I know gases have the weakest attraction, so it can't go there. Liquids are sort of in the middle. The strongest attraction between molecules are in solids. All right, particles close together. They're furthest apart in a gas, they're a little closer together in a liquid, and they're furthest apart in a solid. All right, fixed volume. Well, both solids and liquids have fixed volumes. They don't change. The only one that changes is a gas. So if it falls between two things, you can just have it cross both lines. All right, compressible with pressure. What can you add pressure to and actually change the volume, compress it into a smaller space? That's only a gas fits that one. All right, fixed area. That means it occupies a very fixed space. That is going to be a solid. A solid occupies a fixed area. A liquid can spread out more. Definite volume and shape. All right, that is also a solid. Solids have definite volumes, definite shapes. Liquids more take the shape of their container. Unaffected by pressure. All right, that's going to be both solids and liquids. All right, I'm going to stop right there because now you get the idea of how to do this, and I want you to finish the pile. So pause the video and you finish the pile. All right, I'm going to move on to the next one. Place the following statements under the correct classification. So these are the three formulas that we just used. So if I'm doing Q equals MHF, this is what I want for fusion. So it is either melting or freezing. Q equals MC delta T. Well, that delta T tells me it's changing temperature. And Q equals MHV, HV is when it's vaporizing. So that's when I'm going to use that one. So the first one, break the attraction between solids until they're a liquid. Okay, if I break a solid into a liquid, I am melting it. So I want that one right there. And the next one says melting. So I also want this one here. Changing temperature. All right, this one literally has a delta T, so it's changing temperature. Vaporizing, this one's got the V, so this one's vaporizing. Changing from a solid to a liquid. If you go from a solid to a liquid, you're melting. So that would be over here. Use this formula. Ice to water. Ice to water is melting. Freezing is also over here. Gosh, I have a lot over here. All right, heating up. Heating up implies I'm changing the temperature, so I want this one. Has not melted or boiled. If it has not melted or boiled, that means I'm under the melting point. That means I'm on one of the curves, one of the slopes, so that would be changing temperature. All right, kinetic energy changes. If the kinetic energy is changing, I want delta T. Has melted, but has not boiled. So again, I'm in one of these little delta T spots. Forming steam. Okay, that's vaporizing. So I want that over here. Breaking attractions between liquids until they're in a gas phase. Okay, that's also over here. If I change from a liquid to a gas, I'm vaporizing. Condensation is if I'm cooling it from a gas down to a liquid. Water to ice. Okay, that's freezing. So that belongs over here. Boiling. All right, I'm changing it from a liquid to a gas, so it belongs over here on the vaporizing side. If I'm cooling something down, I want to be here at delta T because I'm changing temperature if I'm cooling it. Water at 100 degrees. So water boils at 100 degrees. So I would want right here. All right, so I didn't mean to do all of them with you, but there we go. We did all of them together. Now I'm going to practice some of these heat calculations with you. So calculate the heat required. So make sure you've got a calculator and your reference tables opened up to table T, and we're going to go ahead and get started on doing these together. Calculate the heat required to change a 50-gram sample of ice from -10 to 0. Okay, I am changing temperature. That means I need Q equals MC delta T. All right, so if I'm changing temperature, I know right away that's the formula I want. I'm going to solve for Q. So Q is equal to, I need the mass first, 50.0. C, I need the specific heat of water. Okay, I am going to show you where to find this. Go to your reference tables and go to the very front. So right now you're really just using the front and the back. The back has the heat formulas. The front, go to table B. Physical constants for water. Heat of fusion, 334 joules per gram. Heat of vaporization, 2260 joules per gram. And specific heat of water, 4.18 joules per gram in Kelvin. All right, so it told me C is specific heat, so I want the 4.18. So every time I do C for water, I want 4.18 here. All right, I'm changing from -10 to 0. So that's a change of 10 degrees. So that's why I need 10. Only in this formula am I using a temperature amount because it's telling me how much I'm changing temperature by. So now I punch it in my calculator. 50 times 4.18 times 10 equals 2090. Now the unit for this is joules, which is a capital J. So that is my answer. If you do get something that has multiple decimal places, you can just round it to the 10th place. This just came out perfectly that way, so I'm not going to round it to a 10th place. All right, let's try this next one together. Calculate the heat required. So again, I'm just solving for Q to melt. So if I'm melting, I want the Q equals MHF formula. So again, every time I read the question, I got to figure out which of the three formulas to use. And I want you to get in the habit of always writing down the formula first. So Q is equal to, the M is 25.0. HF, and it's ice, so that means it's water. So I'm going back to table B. HF is heat of fusion, and it tells me right on this chart, heat of fusion is 334. Punch it into the calculator. 25 times 334 equals 8350. Capital J for joules. That's it. Go on to the next one. Calculate the heat required to boil 340 grams of water. If I'm boiling, I want Q equals MHV because the V is for vaporizing. So Q is equal to, my mass is 340. I go to the reference tables, table B, I look up heat of vaporization because this is water, 2260. And of course, it takes more heat to boil than it takes to melt. It's a harder phase change. So 340 times 2260 equals, big number, 768,400 joules. Now I'm going to show you one more thing with this one, just in case. This is my answer, but in case I wanted to do it in kilojoules, when you have a really big number, you could change it into kilojoules. So to change from joules to kilojoules, I move 3 decimal places over to the left. So it would be 768.4 kilojoules. So I'm just going to put or that. Okay, again, you can keep your answer in joules. I just wanted to show you that it also could be changed into kilojoules. All right, let me do another one with you. Calculate the heat required to change a 30-gram sample of ice from 0 to 50. Okay, I'm changing temperatures. So I want Q equals MC delta T. Q equals, my mass is 30.0. C, I go look up specific heat on the front of my reference tables, 4.18. Change in temperature. If it's going from 0 to 50, that is a change of 50 degrees. I do the math. 30 times 4.18 times 50 equals 6270. All right, I go to the next one. 34,000 joules are needed to melt. Right away, I'm going to underline that melting. 65 grams of a sample. What is the heat of fusion? So Q equals MHF is my formula because I'm talking about melting. And I actually want to solve for HF. So I know Q, 3,400 or 34,000 equals 65 times HF. So HF this time is my unknown. So I'm going to divide this side by 65 and this side by 65. These will cancel out. HF equals, and now I punch into my calculator, 34,000 divided by 65 equals 523.1. So again, it does have decimal places, so I'm going to round it to the 10th place. Okay, this was joules and this is grams. So my unit is joules per gram. 523.1 joules per gram. All right, perfect. You can solve for anything using these little easy formulas. All right, 6,000 joules are needed to increase the temperature. Increase the temperature of water 5 degrees. What's the mass? All right, if I'm increasing the temperature, I've got Q equals MC delta T. And what's the mass? So M is going to be the thing that I'm solving for this time. So I have 6,000 equals, M is what I'm going to solve for. C is 4.18. And I want to change the temperature by 5 degrees. So the first thing I'm going to do is punch 4.18 times 5 into my calculator. And I get 20.9. So I'm going to divide this side by 20.9. And I'm going to divide this side by 20.9. That cancels these off of this side. So M is now going to equal 6,000 divided by 20.9. I get 287.1. And then it's mass. So what's my unit? Grams. Boom, boom, boom. There's my answer. All right. We are moving right along here, people. All right. Next one. How much heat is needed to boil 125 grams of water at 100 degrees Celsius? So this is a great point for you to start pausing me. And when you pause me, go do the work and then make sure you did it right. Unpause me, see if you did it right. So if I want boiling, I want Q equals MHV. So Q is equal to 125 times 2260, because that's the heat of vaporization of water. I multiply that, 125 times 2260. I get 282,500 joules. All right, next one. How much heat is needed to melt? Whoops. Melt. If I'm melting, I want Q equals MHF because heat of fusion is my melting. Q equals, my mass is 350. HF is 334. I do my math, 350 times 334. I get all right, again, keep pausing me. Do this on your own. Make sure you can do it without help. 2,300 joules of heat is required to vaporize. All right, what is the heat of vaporization? So Q equals MHV, and this time I'm going to solve for HV. That might be another good idea too. Every time you do it, you circle what it is you're solving. So my Q is 2,300 equals 120 grams times HV. All right, divide this side by 120, divide this side by 120. 120 cancels off. HV is equal to, all right, 2300 divided by 120 equals 19.2. And then again, this was in joules, this was grams, so joules per gram. There is my answer to the 10th place. There's my unit. All right, 6,500 joules of heat is required to vaporize a sample of water. What is the mass? All right, Q equals MHV, because I have vaporizing in here. This time I'm going to solve for the mass. So Q is 6,500 equals M, and HV for water is 2260. So divide this side by 2260, divide this side by 2260. These cancel out. M is going to equal 6,500 divided by 2260 equals. It only weighs 2.9 grams. Boom, 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 rounding to the 10th place. All right, next one. 48.0 grams of water is cooled from 70 to 25. Okay, I'm definitely changing temperature. Q equals MC delta T. All right, how much heat must be removed? So they want me to solve for Q. So Q is equal to 48.0, specific heat of water, 4.18, and changing temperature. 70 minus 25 is equal to 45. It's changing. So I'm going to do that. It's over here. 70 minus 25. The delta T, the change in temperature, is 45 degrees. All right. So now I punch it all in. 48 times 4.18 times 45 equals 9028.8 joules. There we go. 9,200 joules is used to change 50 grams of water at 25 degrees. What is the final temperature of the water? Okay, so it's changing temperature. So I want Q equals MC delta T. And I know I'm starting at 25 degrees. So start at 25 degrees Celsius. Okay, so first I'm going to use 9,200 joules of water. And this is equal to 50 times 4.18 times delta T. So change in temperature is what I'm finding. First thing I'm going to do is punch in 50 times 4.18 equals 209. So I'm going to divide this side by 209, and I'm going to divide this side by 209. That cancels this out. So delta T is equal to 9,200 divided by 209 equals 44.0. So the temperature changed 44 degrees. So if I start at 25 degrees, I got to add 25 plus 44 because that's how much it is changing by. They want me to give them the final temperature of the water. The final temperature of the water is not 44 degrees. It's 44 plus 25. So that means it's 69 degrees Celsius. That would be the final temperature of the water. 25 plus the change. All right, now my work with you is now done. You are now going to go do 3 problems yourself. These should be different from every single person in the class. Do not do the same work or work with somebody. You can work with somebody, each come up with your own problems, and then practice. Make sure you can do their problem and they can do your problem and get the same answer. But I want you to do a problem for a melting problem, a changing temperature problem, and a boiling problem. Oh, you guys, this is a mistake right here. So this should say Q equals MHV. So I want you to do one of each. So on the next 3 slides, do each of those 3 problems. And when you're done, any questions? And these are the learning targets. So this is what I want to make sure that you can check off that you have learned today. All right. Thanks, everybody. Have a great day.